Okay, so let me share my slides. Think so okay, so let's go to that slides. Hmm. So, good evening, students. Welcome to the live interaction session of NPTEL for Sustainable Power Generation System. This is live session 4 being conducted on 28th of August. The course is taught by Professor Pankaj Kalita and he is Associate Professor in IIT Guwahati. I am Rohit. I will be taking this live interaction session for you guys. So let's start this session now. This is my introduction for this T-shape and the methodology we follow. So we will follow the same methodology that we have been following in the last three class. Like we will be first discussing the topics that are taught in important topics that are taught in weekly lectures, and then if there are any doubts arising out of that, then we will go to that doubt, discuss those doubts also. Apart from that, you can also ask your questions. So sometimes because I have shared my screen, so maybe I am not able to hear you guys, so you can write it in the chat box. I will read those chats in the meanwhile, and then I will answer your queries. Okay. And also you are also encouraged to post your questions on the discussion forum so that will be able to read your questions and answer them properly. Okay, so if there are some questions which require more discussion, or you can say more people can benefit from the answer, so please post it on the discussion forum also. Okay, or if you have any queries related to technical queries of this course, so you can also post it on the discussion forum. So please use the chat box freely, and use the discussion forum to also to get your queries addressed. Okay, so this week is very interesting. We have been talking about the solar thing in the past. So solar, we talked about the overall generation of energy through renewables and unconventional resources. Then we moved to solar energy. Then there were two brackets of solar energy. One goes to this thermal thing, solar thermal, and then we moved to solar photovoltaic, where we use a solar photovoltaic cells or modules to convert directly solar energy to the electricity. So similarly, one such another device of energy conversion, that is energy conversion systems, is wind turbine. So wind turbine is what I can say is a very important or significant device which directly converts the power of the wind, like the energy content of the wind, or the kinetic energy, I could say the exact term, the kinetic energy of the wind directly to the electricity. So this is one of its own kind of thing, or own kind of device or instrument, you can say, that converts one form of energy to another. Okay, so we'll study this wind turbine thing throughout this lecture. We'll go in detail. I think not as much detail as it was discussed in the lecture slide. So if you have any queries of which you want to get further clarified, so I suggest you guys to please refer to the lecture slides. Those contain a lot of information about how to calculate the energy, how to get the rotor speed or different parts of wind turbine. So I will discuss some of the slides here. Otherwise, you can also refer to the lecture slides and lecture videos for a good and better understanding of the concepts. Okay. So when we talk of wind, so what is a wind? So we are generally very much concerned about what consists of a wind. Is it air or is it different from air? Okay. So wind is something, you can say, which flows. Okay. So if air flows due to the pressure created in the atmosphere is wind. So how does this pressure actually created. So this pressure is actually created because of solar thermal heating, because we receive solar energy, then what do you say, undifferentiated heating at two places leads to variable pressure between these two places, and due to this variable pressure, the air flows from high pressure to the low pressure area. So this is what happens in case of wind. So, what researchers or scientists or inventors determined कि yeah, this can easily be harnessed to generate electricity. So this is I repeat this word this line again. This is not a new concept developed in this century, because earlier also, I think 2 3 centuries earlier also, there were technologies which were harnessing the power of wind to draw pump water from the bore wells, or you can say in India also we see some of these wind related energy conversion systems where wind power was used to uh, what you say, grind the cereals or wheat. So these type of things were there. Okay, so these now the wind turbine which we see in today's world are quite advanced, quite advanced and quite large in shape, not like the earlier world where they were in a small shape, not so small also, but they were in a small shape and were very low power generation systems. But now they a single wind turbine can generate up to 2 megawatt of power also. So that's a very impressive thing which we have achieved. And the main thing is that ki when you go for solar, okay, so if you have to install a solar power plant, then you have to cover all these fields with solar cells. But in case of wind turbine, this is not the case. You erect a pole, you put a wind turbine, that wind turbine revolves and then it generates electricity. So in the land, meanwhile, you can always go for agricultural or any other purposes. Okay, so that is the beauty of this wind turbine or this wind energy generation systems. Okay, now the second thing which I want to discuss here. So these wind turbines are huge. They are really huge. Okay, so you can see this is a house. Okay, you can see a structure build up here. Okay, so probably this is some transmission or generation system will be there here, which will collect the electricity and transmit it to the nearby substation. So you can imagine the height of these structures. So generally, these structures are 80 meter, 100 meter of height. How you can imagine the large, how large they are, and these blades which you see here. So these are actually aerodynamically shaped so that we can harness more and more of this wind energy to generate electricity. Okay, so this is what new every day we get a new type of things working into the improving the rotor blades, improving how electricity is generated, improving the yaw mechanism, the nacelle, the different parts of wind turbine, the portion of this pole which supports the wind turbine. So all these things go into a lot of research nowadays to generate or harness more and more of wind electricity. But the problem is that there is a beds limit. So I will discuss that limit also. So you can only harness a particular percentage of that wind energy only. So there is a total theoretical calculation for that. So you can refer to that calculation. But there is a beds limit up to which you can harness the kinetic energy of wind to convert it to some other form of energy directly. That is mechanical form of rotor energy. So this wind energy not directly converted to electricity like in case of solar photovoltaic. It is first converted to rotor energy and then it is converted to electricity. Those rotor rotates and the generator is clubbed with there, so it generates electricity. So this is how it goes into work. Okay. see if there are any questions. Okay, so if there are any questions or anything, guys. So these I want these lectures to be interactive. So these are not like one-to-one lectures or something. So I want you guys to share your understanding of the wind energy, or have you seen any wind energy devices working in nearby your area, or do you imagine something where wind energy has been harnessed, not like a wind turbine or anywhere where you see wind. What is wind pumps for water pumping? Are sir, what is wind pumps or water pumping or drainage? Uh, Sorry, Kedarnath, I could not understand your question. So, what is wind pumps? So, are you asking about wind pumps? Water wind pumps or water pumping or drainage? Okay. So, okay. So don't worry. Wind pumps. I will tell you actually. So, what happens? So let me tell you here itself, so your query can be answered. Do I have a slide? Yeah. Or let's say water wind pump. So we have this wind turbine. Okay. So this wind turbine rotates actually. So there are two designs for wind pumps actually. When you say wind pump, so there is a pump here. Okay. This pump is connected to some rotor, as a normal pump is also connected to electric rotor. Okay, electric motor you say. So this pump is connected to some motor, and this motor in earlier times what happened? There is a shaft here. So this shaft is directly connected to this rotor shaft here. So there are gear mechanism. So you say a gear mechanism is here where this rotates because of the motion of the rotor. Okay, this rotates like in the clockwise direction. So this shaft also rotates, and there is some powertrain devices which connects it to the pump rotor. Then this is pump, and this is input of the pump to some bore well, okay, or some water reservoir body, and water, because of the rotation of this shaft, the water moves into this, and then you can have the water output here. This is how it works. So this is one design. Another one is that this wind turbine generates electricity. So instead of having a separate electric motor here, this electricity is directly fed to the. You still be needing a motor. Sorry. So there is a separate motor for pump here, and this electricity generated is directly fed to this motor, which rotates the pump, and then it draws the water, and then water is supplied at the outlet. So these are the two designs for a water pump. Okay, where wind energy directly used for water pumping. Pramod has raised a hand. Uh, yes, Pramod, you can go on. Good evening, Pramod. Why do we why do we use water? Why do we use water for what? In the wind turbine. No, we don't use water in the wind turbine. So Kedar was asking about this, how wind turbine is used for water pumping. So that is what I was explaining. How wind turbine can be used for water pumping. Okay. So there are standalone system, wind energy system that delivers water, similar like solar water pumps. So in the last lecture you heard about this solar water pump, na? So where solar electricity generated from solar energy that used for pumping water from the ground. So similarly, this wind turbine also generates electricity that can be used for pumping water from the ground. So this is the concept. Wind turbine doesn't use any water. Okay. Wind turbine only use wind to convert it to the electricity. Solar cell use solar energy to convert it to the electricity. Hydroelectricity, that is dam, uses water to convert it to the electricity. Okay. Okay. Any other questions? Guys, please, if you have any questions, please put forward anything which you don't understand or you want to discuss something. Like if you I would say, like, I want you guys to list one or two devices where wind energy devices or anything where wind energy is actually used. List any one or two, anything which you can think in your mind that yeah, wind energy is actually used here. Wind is actually used here. Can you think of anything like this? Think for 2 minutes. Think where wind is very much important. If there would have been no wind, then that thing is not possible at all itself. In Yeah, that's exactly that is what I was thinking on that lines. Oh, very good and fantastic answer. All the aeroplanes, all the not turbo aeroplanes only. Turbo aeroplanes work on that concept only. Turbo, then aerodynamics, shape, and all those things. The rotator. Even if you have a jet plane, that also works on the wind. It glides on the wind because of its aerodynamic shape. Okay. If there is no wind, do you think plane could fly? No, it can't fly. Okay. Unless it is designed in such a way to operate in as a rocket. Okay. So if you it can go vertical only. You have to if you have to move it in the this direction horizontal shape, then the design has to be modified in such a way. But normal planes are designed in such a way that it uses the aerodynamic flow of the air throughout its body to glide through the air and move forward. Okay. So this is one example. Another example is kite. The kite which we flew in our childhood, that is also a wind device. There, if there is no wind, do you think kite can fly in the sky? More wind is there, but there is a catch here. If there is more wind and wind flowing at a very high speed, like in case of storm, so do you think kite could fly? It can't fly. And there is always a chance that these kite will break down from string and go away. So similar is the case with wind turbine also. So there is a limit up to which it can generate electricity, but beyond that limit, the electricity generation has to be stopped, because if rotor rotates at that high speed, then there is always a chance of accident, and that will not be good for the economy of any company, because if any damage occurs, then it takes a lot of time to repair the wind turbine, and the cost associated with it is quite huge, amount of labor and all those things. So this is what it happens. Okay, so we'll move forward. Yeah, please ask. Acha, how electricity is transmitted? So that is quite a different concept altogether, which comes in the electrical engineering domain. But I will give you an idea. So let me explain how electricity is transmitted. So what is your background actually, Pramod? Mechanical engineering. Okay, so that is why I think you are getting a doubt like how electricity is generated. So you are more concerned because mechanical engineers are more concerned about how electricity is generated. And then there comes the work of electrical engineers, how that generated electricity has to be transmitted. Okay, so don't worry, I will explain that also. So what happens when a wind turbine generates power? Let's say I will explain it with a block diagram. So let's say this is a wind turbine. It generates a power. So generally what happens, this power is generated in the form of DC current. Okay, because wind turbine rotates in a single direction, so it generates in the form of DC current. So this has to be, actually you can store the power. Okay, so if you want to store the power, there has to be some connection with the batteries, because electrical power can only be stored in the battery. But in case of wind turbine, what we do, we generally transmit this power to uh, converting it in the form of AC power. So we have a converter here, then we convert it to AC power, and then we transmit it to the grid, nearby grid. Okay, so there, let's say this is the grid connection. So these power lines are connected to the grid. So it gets transmitted through the grid. Okay. Otherwise, if it's a standalone system, then you can store the power in the battery and you can use it is as you use it in the house or something. Okay. Okay. But generally, wind turbines don't need battery. Can anyone comment on this? In general, wind turbines, they have batteries also, but not uh, not required as of such. The reason is that wind turbines, even at very low velocity of operation, like 0.5 meter per second or something, not zero point 0.5, I think 3 or 5 meter per second of operation or something. So you can check the values. Very low wind speed also, because of gears arrangement inside. So there is a long rotor, then the very small gears are there. So because of those gears arrangement, I think mechanical background students can relate to that very easily. So because of those gears arrangement, these wind turbines generally generate electricity even at low wind rotating speed, low wind speed. So that is why we generally get a continuous supply of power from wind turbine. Okay. So this is one of the benefit of this wind turbine, installing a wind turbine, because a proper survey is there. Yeah, this much wind speed is flowing throughout the year or throughout the day in this area. So let's install a wind turbine there. Okay. In case of solar energy, the problem is there. We can have a survey for that. But the problem is if you have a survey but there is a night, so you don't have a solar at night. But we can have a wind at night also. Okay, so we generally get a yeah, Kedar, go on. Wind turbine converts kinetic energy of wind to the mechanical energy, then mechanical energy to the electrical energy. Okay. Any other doubt? Okay. Okay. So let's move. I think I had a lot of slides, but yeah, it's good discussing with you guys. So you guys could uh, give your views on the wind turbines. So yeah, we'll discuss a lot in the meanwhile. Let me take a photo of this. So this is what I was discussing. Now early wind turbine design. Okay. So this is what I was talking. In medieval times or post medieval times, the wind turbine looked like this in 18th century, 17th century. Okay. So this wind vanes, we can say, this was actually used to grind grains or to draw water for the fields. So this was already there. This is not a new concept. So this has been improvised to this. Okay, so this is one of the horizontal wind turbines. Why it is called horizontal? Because the axis is horizontal to the wind flow. Okay. Now this is vertical wind turbines. So axis is actually perpendicular. So wind will flow like this. The axis is almost perpendicular, similar like this. So this is Savonius type rotor. This is Darius type rotor or something. You can interchange also. Check in the slides. Okay. Now the question is, which of these produces more power? Why do we see more of these and less of these? Most of the wind turbines are like this only, na? But still, why do we see more of these? Not this type of designs in wind turbine. Can any one of you could comment on that? Any guesses? Like which one generate less power? The vertical one or horizontal one? Vertical one. The yeah, exactly. What happens? The more we are more, but if you see the like power to weight ratio or something, so vertical one generate more power in the normalized fraction. But overall, the power generation from horizontal turbine is much more than the vertical turbine. So that's why we go for horizontal turbines. But one of the main drawback of using horizontal turbine is that noise. If you go to a wind turbine farm, you will observe like it has a aeroplane like sound. The the rotor moves in such a way that it produces a lot of sounds, and the natural ecology, the birds, they actually get disturbed a lot because of this. So yeah, there are some environmental, but the vertical type of turbines, they are very silent in operation. Okay. Yeah, Pramod, do you want to ask something? Why? How does or why does vertical one generates less power? Huh, okay. So see what happens. And because see, power generation is like there are some kinetic energy which has to be converted. So let's say kinetic energy of air is 1 by 2 ABQ, and then there is this rotor blade area which it covers. So you can see the blade area which it covers is quite high compared to this vertical axis turbine. So this is one of the reason for less power generation. Another is that this the interaction between wind turbine and the air is quite high in those vertical axis turbines. Okay, so that is one of the reason. Because of less interaction here, the production is quite less here in a vertical axis wind turbine. Okay, okay. So let's move to the next slides. So wind machines can be classified into based on axis of rotation or rotor diameter. So rotor diameter you can see micro, mini, domestic, commercial based on the diameter of the rotors. The important ones are vertical axis wind turbine and horizontal axis wind turbine, which you saw. In vertical axis wind turbine, there are drag based turbine, that is Savonius type, lift based, that is Darius type, and then in lift based also we have egg beater and gyro mill, and there is also H rotor type like drag plus lift type also. So you can always go to Google and search these terms, and you can see the photographs, the images, how the wind turbine look for these type of things. Okay, so different type of windmills are there. Now we are talking about windmills. Okay, so I was talking about this gyro mill or egg beater. So some of the pictures are here. This is Savonius type rotor. This is gyro mill. Gyro mill like flat panes which moves. Okay. This is Darius type rotor. So I think this is Darius. This is Savonius. Okay. And this is Magnus type rotor, where this axis also rotates and these rotors also rotate. Okay. This is vortex type rotor where air flows and then it creates a vortex to rotate the blades inside. This is downwind. This is upwind. Upwind is the wind turbine. The rotors faces the air first, and downwind the air approaches from back. So nacelle is the first thing of contact between air and wind turbine. The farm faced multi-blade wind turbine where you have too much of blades, triple bladed, double bladed, single bladed. Okay. Now, because a convention is there, we use a triple blade wind turbine. So it is a settled convention. So there has been like power generation ratio to some the force or lift or drag, everything has been considered, and then it was settled that three bladed wind turbines are quite good for power generation. So that's why we use three bladed wind turbines. Now comes to the component of wind turbine. So wind turbine is basically is there any questions? Yes, Pramod. Huh? Windmill. Those are upwind turbines. Upwind. Okay, the design is such that the air first directs comes in contact with the rotor. They are not designed in such a way because from the back there is what you say a structure is there. So the approach of wind cannot be in such a way that it strikes the rotor first. Okay, from back. So they are generally of upwind turbine. Okay. Okay. So components of wind turbine. One is this rotor. So this whole thing is rotor, and these are blades. So these blades are aerodynamic shape. So a lot of discussion in I think lecture 3 or 4. The aerodynamic shape, the camber, what is camber line, what is maximum camber, mean camber. So please go through those lectures. So understand the aerodynamic of the wind turbine. Then you have a brake. So brake, why brake? Because of very high velocity you have to stop the wind turbine so that to prevent it from any damage. So there is a brake. Okay, this is the gear or yaw motor. So yaw motor is like because air can come from this direction also, this direction also. So this yaw motor aligns the wind turbine to make the air strike perpendicular to it, to the blades. Okay, so this yaw drive basically tracks the air movement and then aligns the rotor to the direction of the wind. And yaw motor is there, generator is there. Before generator you have gearbox. So this is the main shaft, this is the big gear, and these are small gears. So if let's say this gear rotates at 10 rpm and the gear ratio is let's say very small gear, this is a gear ratio of 100. Okay, so this is 10 rpm, this rotates at 10 rpm, very low speed, 10 rpm is like this. Okay, but since gear ratio is 100, so how much will be the speed of this gear? This will be 10 into 100. Okay, so 1000 rpm. So you can imagine this, even if the wind turbine blades are rotating at a very slow speed at 10 rpm, this generator is actually rotating at a speed of 1000 rpm because of very high gear ratio. Okay, and because of very high gear ratio we get a good amount of electricity produced by the generator. So there is controller also, this whole box in nacelle, and then this power is generally transmitted through power cable to, there is a transmission instrument placed near the wind turbine what you say base. Then through that it transmitted to the grid, local grid, or for other purposes. Okay, so I think someone has any questions. Let's see. Okay, any questions from you guys? Anything which you want to ask? What is the material of gear? Blade. Generally, see, earlier the blades were made of aluminum. So aluminum was the preferred material. Why? Because aluminum has a very high weight to strength ratio. So aluminum, but nowadays I could see that they are making of carbon fibers also. So a lot of work is going on in the carbon fiber field because they are very lightweight. So as of now, aluminum is the preferred material. So not if you say is it purely aluminum? No, it is not purely aluminum. It is an alloy. Okay, so there will be a lot of aluminum also, maybe some other elements also. Okay, okay, and any other questions? Hmm. Okay, so this is what I was talking there, and I show you guys now. There is a break here, a break here. So what happens in case of there is a proper cutoff channel, there is a proper area. Uh, if I could say, let me draw that here so I could explain to you guys in a better way. So if you see the wind speed, so let's say this is wind speed and this is power generation. So power wind speed is zero, power generation will be zero. You all agree? Then it moves like that. Okay. So then this is the area where constant power generation happens. Then after this, the power generation becomes constant. Okay, this is like constant. Okay, this is not down. And then there is a very high. This is a cutoff wind speed. VC you can see cutoff speed of wind. So after that, the wind speed are very high. So wind turbine is stopped by applying the brakes, so that damage to the wind turbine could be avoided. So in case of storm which has a very high velocity like 25 above 25 meter per second, so wind turbine operation is generally stopped. Okay, so this is the area which is the main concern of our study, where the maximum wind power is generated. Okay, I hope it clears your answer. Is it okay, Kedar? Okay. Any other questions? So should I move ahead? This seems interesting. Okay. So this is simple thing. The vertical distance between the rotor, that is this is a rotor, and between the center line of the ground is actually tower height. So this tower height is a very important meaning. So because as you increase the height of tower, the power generation capacity will be increased. So with the same dimension wind turbine, if you increase the height, more power will be generated. Why? Because wind speed is increased and more consistent wind flows in the upper atmosphere. This is fiberglass. So this is what Pramod was asking. Ki, sir, what is the blade materials? So yeah, this is fiberglass reinforced polyester epoxy. So these blades are made of like this. Okay. So more and more research is actually going on. The carbon fiber or aramid is also used. So this is actually the main. Earlier it used to be aluminum. Okay. Or an alloy. So this is actually an alloy or based on various types of new composites. Okay, wood compounds, wood epoxy, wood fiber epoxy is there. Okay, this is generator, this is hub. Okay, right. Yes, Pramod. Yeah, but this PPT is shared with you guys, na? Do you don't you get the PPTs? I'm surprised. Is it? Let me check. So you log in like this on the mobile or something. You go to my courses, then you go to the sustainable wind power generation system. Okay. So you go here, problem solving session July 2024. Okay. Click here to view the problem solving session slides. So this page will be opened. So this is from the Kapil. Two TAs are there. One is me, one is Kapil. So you can refer to any of us. Okay, that's not a problem. So the sessions like week 3, like last week session. So you can get this session from here. Okay. Okay. You can see the recordings of the last week session. And it's playing. Yeah. You can see last week it was photovoltaic cell. So the recordings are totally there. Everything is there. The question which you have asked, everything. And the slides, for slides, you can click here, presentation folder link. So I generally upload week 1, week 2, week 3. I will upload week 4 today. So you can access it from here also. Okay. So now you got it now. How do you access these slides and presentation? So you go to the course page, you go here, problem solving session. Even the mobile app also shows similar link, the problem solving session recording link. So click on that problem solving session and then click here to view the problem solving session lectures. Okay. Okay. Uh, okay. So let's move to the next slide. Okay, now the working principle. So I don't think working principle is actually needed because the whole discussion which we are doing from 1 hour is basically based on this working principle, how wind turbine electricity is generated. So Pramod or Kedar, do you want to have a take on how wind turbine works, seeing this diagram? Let's say this is the wind turbine. So how do you think this electricity is generated? Anyone, Pramod? Okay. So simple. Okay, so the first thing is that wind strikes these the rotors. So if it is upward wind turbine, the wind will come from this. If it is downward, then wind will come from this side. So it strikes the rotor. Because of it striking the rotor will rotate. So what it is doing, turbine blades capture the kinetic energy of wind and convert it into the torque. So torque is what? Torque is a mechanical energy, rotor energy. So torque, so this shaft is rotated, so there are gear mechanism here, gearbox. Then because gearbox is actually connected to the shaft of the motor, so generator, so power is generated and this power goes to this lower part of the basement of the tower, and from the basement grid transmission occurs when it goes directly to the grid. Okay. So low speed shaft connected to rotor gearbox, these things are useless, you can study. So from low speed high torque to high speed low torque. Okay. Yawning mechanism allow wind turbine to rotate on its vertical axis. So this is the vertical axis. So based on vertical, orient the rotor in the direction of wind, maximizing the energy capture. Okay. Rotor and nacelle sit atop a steel and concrete tower. So this is concrete foundation and this is steel tower. Power density curve. So I think uh, I can discuss up to this and then can have a good discussion on that. So power density duration curve. So this is power, this is duration. So what happens when you see a wind turbine or wind? So this is cut in speed. So speed below which there is. Someone. Okay. I thought someone is asking question. Okay. So what happens because of the this I show you. So this is the cut-in speed. Is there someone who joined or any questions? Um, no. Uh, is there any question anyone wants to ask? Okay, I think okay. So if there is any question in between, you can always raise your hand and ask, or you can unmute and ask, or otherwise you can post it here in the chat box also. No problem. Okay. So this is what happens. Cut-in speed is that key below which the power won't be generated. So there is always a cut-in speed for power to be generated. Okay, why? Because there are some drives, gear drives also. So it requires a minimum rotation for generator to generate power. It doesn't generate power at 1 RPM, 2 RPM. There is some minimum rotation needed to generate power. Now design speed is rated speed. Okay, so that rated speed is what a constant power is generated in that duration. Okay, then cutout speed or furling. So wind speed at which it is advisable to shut down the machine in order to avoid mechanical damage. This is the speed where the power of the wind or kinetic energy of wind is so much, like in the case of storm or some that. So this is the speed at which no power is generated. So if you see there is this cut-in speed, then there is a design speed, or you can say power density curve, then this is cut-in. Okay, so this is what the area which covers the total power generated. If power density curve is like this for wind turbine, okay, and this is where no power is generated, so total area in the curve in this region is the amount that is generated. Okay. Now the Bates limit. So a scientist named Bates, so he said that no wind turbine could convert more than 59.3% of the kinetic energy into the mechanical energy. So is a proper calculation. How did he achieve this limit of 59.3%? So you can go to the lecture slides and see the calculation. Professor has explained it very beautifully. So if you have a wind energy like 100, like you say 100 kilowatt of energy in the wind, the maximum energy you can get from the wind turbine is actually 40.7 kilowatt. Okay, sorry, 59.3 kilowatt. 40.7 kilowatt will be lost always. Okay, and then if there is 70% of conversion of this energy to electricity, then multiply 59.3 into 70%, so you will get 41% as the total energy that is actually converted to electricity. So that's a very good efficiency. You know, efficiency of thermal power plants, so they work in 35-40% efficiency. So more than that is getting the efficiency is even more than that of a thermal power plant if you install a single wind turbine. So it is converting 41% of energy in the wind to the electricity. Now estimation of wind energy output. So this I think before I discuss this formula, we'll solve numericals and use these formulas to make you more acquainted. Okay, I think two slides are there, mode of wind generation. So we can discuss it later also. So before we proceed to assignment questions, if there are any numericals or anything which you want to ask, so please feel free to ask your questions here. So let's take a break from lecture slides of 5 minutes and let's discuss. If there are any questions, please write it down here in the chat box so that I can read and then I can answer. Or if you want, you can also unmute yourself and ask the question. So for that, I will say, please go. Let me put these lecture slides on the screen so that you guys can actually see the, let's say, working principle. I put it here. So if there are any questions, please feel free to ask. Okay. The question which Kedar asked. Okay, Kedar asked one question. Okay, let me see. Kedar, one question Kedar asked. Sir, please once more teach power density. It's very easy, Kedar. You don't have to look much into it. See, there are three speeds. Cutting speed, you know. So before cutting speed, like say this. This is for whole duration. Ignore this. Ignore this curve. Let me take a slide here. You will get this curve. You will get this curve through this formula. Okay, use this formula. You will get this curve. And even if you don't use this formula, no problem. Let me take a slide here. Okay, so what happens, this is power and this is velocity. Okay, so I am talking about power and velocity. So earlier it was power and with duration, so that is also okay. Hour per year. So this is power. What happens, there is some, let's say 0 and then 5, let's say this is 25, and above 25 no power will be generated. Below 0 to 5 no power will be generated, because about 20. So I am taking this hypothetical value very near to actual values, so you can verify them. So after 25 what happens, brakes are applied, no power is generated, and before 0 to 5 power is generated but very low, like speed goes on like this, but it's not a very, you say, a constant type of power. So it goes like this. Okay, then between these two the constant rated power is generated. Okay, so this is the actual power output, and then after this no power is generated. Simple, no power, no curve will be there. So this is what it says. Cut-in speed is this. Okay, 5a. Rated speed, design speed, this is rated speed at which we get a constant power. Okay, produce a rated output, you held constant at the rated value for winds, and then cutout speed of furling. So this is cutout speed. No power will be generated because brakes are applied to save the wind turbine from damage. Now, if you see this curve, kilowatt hour per meter square. So what happens? Eraser. Hey, why it is not erasing here? Discard. Okay. So what happens? So you go throughout the hour per year. Okay. So as you see, this is the area where there is cut-in speed. So this is where we don't have any much power generation, or this is, then this is the rated speed. So within the duration, if there is variation in the wind speed is there, so this will be the power is generated. Okay, and then there is cut-in speed where no power will be generated. So actual power will be between this. Okay, a sorry ke d g h, this is the actual power. So this is where the maximum the power generation will, when you integrate this area, the total power generated by the wind turbine will be there. Okay, so this is depending on the duration, and this is with wind speed. Oh, actually it goes on. So both of these are correct graphs. Any other questions? Okay, Pramod, is there any question? Yeah, you are audible. Yes, sure, ask. Where value of V was increasing where? Huh. In this sheet now. Okay, let me draw it once again. So this is power, this is power, and this is velocity. So I am saying, okay, between these the V actually increases, so power will reach a cut-in speed where the actual power generation will take place, and this, and there is no power. Okay, so this is the power of the wind energy. Okay, the power content in the wind, it doesn't mean it will translate to the power, wind power electricity generated. Why? Because it is below the cut-in speed, the rpm will not be enough to rotate the shaft in the generator to generate electricity. Okay, Once it reaches the curtain speed, the the wind turbine is designed in such a way that it operates at a rated RPM. Okay, so because of that rated RPM, the constant power will be generated called design power or rated power in this area. So if you get the area between this is the actual where the power will be generated. Now after this, there will be cut in, no power will be generated. Now ask. Even if you increase the wind speed goes above this, the rated RPM will be remain same because this is a designed speed, na. Okay. Yeah, that I understand that I understand your concern. What you are saying, ki even if you increase the velocity, the power in the wind is actually more, so more power should have been generated. I agree with that. More power should have been generated, but the wind, the whole system is designed in such a way so that it operates at a rated speed. Called rated. You can see the design speed. So if speed is same, then when you apply this formula, where you get the power 1 by 2, the CP value coefficient of power will be same for a single wind turbine. Okay, density of wind will be same, area of rotor blades will be same. What is varying here? The V. So if V is the rated speed, VR, let's say, so power will always be same. Okay, this is design speed or rated speed. Okay, so doesn't mean that if wind speed is increasing, so generally what happens ki wind speed increases, then it remains normal to, like you see in case of wind flows at a, let's say the pressure difference is there, so wind start flowing, but a time will come when wind will have very low fluctuation, it will flow at the same speed. Okay, for a long duration time, for 1 hour it will be flow at the same speed itself. So this is the speed which we are targeting. Okay, call, can I go to the next slide? Yeah, this one, bed limit. Okay. So what happens? See, bed limit says कि if wind has a 100 watt of energy, ठीक है? So bed limit is saying कि only you can get 59.3 per watt output from the wind turbine. Okay? So wind turbine gives output in the form of mechanical energy. You agree? Called rotational energy or rotor energy. ठीक है? Now this kinetic energy is 100 kilowatt of wind. You are getting 59.3 watt of rotational energy. Now the shaft rotor are connected to generator. Then there is motor and everything is there. So it is saying only wind turbine converts. Let's say wind turbine the generator efficiency is 0.7%. So if generator efficiency is 0.7%, then 59.3% is actually multiplied with 0.7%, 70%. That is comes out to be around 41. So this is the actual electricity output. So out of 100 watt of energy content in the wind in form of kinetic energy, we are getting electricity that is equal to 41 watt. Okay. So total efficiency and overall if you calculate, that is 41 output upon input, that is 100. So it comes out to be 0.41. Understood? What is 70%? See, 70% is the efficiency of the gears plus generator, everything is taken into account. There will be, let's say, let me show you here. I think here you will. These rotors will rotate at let's say wind is striking. Wind has some velocity and it has 100 watt of energy. Now these rotors will rotate. Bed limit say कि at this rotor, you are only going to get 59.3 watt. That is the maximum limit as per Bed's limit. Now there are some gears also here, some generator also here. These will have some efficiency of conversion. So the question says that this is going to have 0.7%. So whatever it is receiving as input, that is 59.3, only it will convert 0.7% to electricity. Now you got my point? Okay. I think we should teach with diagrams so that more and more clarity should be there. Okay. So this is power formula. Not much to discuss. This is standalone on grid mode, grid connected. So this, I think this is also not required at this stage. Uh, okay, so we have some questions of like objective type question, and then we have some numericals also. So we'll solve that also. No problem. We'll, and if there is any question, okay, no question from Kedar also. So let's start the assignment questions. So, guys, I will try to go fast because these are very one to single line concept type questions. So, I think if there is anything which you want to discuss, so please tell me, sir, please discuss this. Yawning mechanism is employed into a wind energy converter system to control wind speed. No. Stop the wind rotor. No. Control electricity generator. No. Keep the rotor in the wind direction. So, this is what a yawning mechanism is. This. So if wind is coming from this direction, so yawning bearing system gears are there. So it makes sure it aligns the rotor blades perpendicular to the wind. So let's say wind is now coming to this direction. So it will move the nacelle to this direction. Got my point? How it does? So there is some planetary, not planetary, there is some gear mechanism. So there are gear and some electric motor is there that moves the whole nacelle or hub towards the arranging towards the uh, direction of the wind. Okay. So this is whole, you can see the diagram and you can also refer to it. Uh, yeah, I mean, wind turbine changes orientation. Okay. So it doesn't mean that it will move throughout 360 degree. It doesn't move like 360 degree, but it arrange even vertical movement is also there. Okay, I'm talking about the horizontal movement here. Na, horizontally it moves from this to this. No, it also moves vertically also. So there are arrangements. Okay, 80% of the bed limit is equivalent to. Now you guys will answer this question. Still, I haven't calculated na. You calculate and tell me the answer. Bed limit how much is the bed limit? 59.3. 80% of 59.3 is so the correct answer is 47%. Tip speed ratio is defined as, so tip speed ratio tip. Okay. So whatever you are getting at the rotor tip to the speed of wind is tip speed ratio. Okay, this is very important. This is actually used in many formulas to calculate the power output also. So the ratio of the speed of rotor tip. So whatever you are getting at the rotor tip, not at the rotor root. Okay, rotor tip. So this is rotor, so tip. Okay, to the wind speed. So correct answer is answer C. The given wind speed on a place is 10 meter per second. The blades of the wind turbine are 35 meter long. How much wind power can be generated from the machine? So calculate it and tell me the answer. So let me give you a hint also. Okay. You got the formula na? Use this formula to calculate. Yeah, but let's assume that for this the CP value is 1. So CP comes into play when there is a particular wind turbine or blade type is defined. Okay, so it is saying how much power is there in the wind. So for wind, you need to calculate the power of the wind. So that is, this is the formula rho AVQ. This is the formula of the kinetic energy of the wind. Simple. Calculate it. Take your time. Ah, answer is 21.35. Is it? Are you sure? Ah, 23.66. How you guys is getting? It should not be 23.66. You must have been taking some unit wrong. How much is the A area? Pi r square. Pi r square pi into 35. That is 3.14 into 1.1225. Okay. V. How much is the value of V? 10 meter per second. I think 10 meter per second, then cube 10,000, sorry, 1,000, 10 into 10 into 10. And how much is the row air? 1.23 kg per meter cube. 23, 2.366 is the correct answer. So correct answer is 2.35. Okay. So I think Kedar and Pramod, do you guys got the answer correctly? Anything to discuss here in this question? Okay, so yeah, Kedar, you are trying, no problem. Please try, Kedar. Okay, if you are facing problem, please ask ki, how did we solve this? Because I am here for that only. If 2.36. So this is 2.36. Did you got it? Kedar, did you got the answer? You got it now? Okay, then we can move ahead. Okay, now solve this question. A wind turbine has three blades, each 4 meter long. At what distance does the tip of each blade travel in one full revolution? It's a very simple question. Just you need to see what this question is actually asking. So let's say if a wind turbine is there, it has 4 meter of length. And okay, you got it now, Pramod. Let's help the Kedar also. So how much distance it is going to travel? So this is the r, okay? This is radius. So how much distance it travels? 2 into pi into r, okay? So Kedar, can you calculate? How much is the answer, Pramod? Correct. Let's wait for Kedar to calculate. Got it now? Okay. Let's move to the next question then. This is also a numerical. I guess you guys will be able to do it. Let me write the formula here. Capacity, what is capacity factor? So plant has a rated power of 5 megawatt, so it is producing 5 megawatt. The annual capacity factor is 0.31 and the efficiency 36%. The annual electricity generation. So capacity factor what is? Annual electricity generation, that is annual electricity output upon the rated power of the plant, and because it is calculated for a whole year, so you need to multiply it with the time also. Okay, so you can, how much it is? That is 4888.1. So Kedar, did you got the answer? You got it now? Okay. Now we move to the next question then. How much is the time remaining? It's 8:38. Okay, we have ample amount of time. So wind velocity at the height of 90 meter is 9 meter per second. Power law index is zero point 0.3. The wind available at height is 140 meter from ground. So now you have to determine the wind available at the height of 140 meter. So what is the formula for this? U at 140 meter is equal to U at 90 meter into जो earlier new height by earlier height to the power. How much is the power law index? That is, you will get here alpha, that is 0.3. So put the values and get the answer. Okay. So these formulas you have to remember. Okay. So this formula is like uz into uh into z upon h to the power alpha. So you have to remember these type of formulas because very straightforward question can be asked in the exam. So if you are not comfortable doing these type of question, these are just one line apply formula, get the answer. You can't afford to miss these type of questions. How much is the answer? 10.27. Correct answer. Did Kedar also got the answer? You got it? So, so did you, are you guys enjoying solving the numerical questions now? Is it easy? So this is what you apply your concept to the question. You just have to make sure ki you applied the concept and get the answer. That is what it is done. So a lot of numerical has been done. Now we'll move to some theory questions. So relax you guys. So make you guys relax. Then we'll solve one big question. So I will let you guys solve that question. I won't give any hint to that question. You guys will solve that question. Otherwise, after 5 minutes, I will solve that question, and then I want you guys to solve this question. Based on the type of rotor, the turbine used for vertical axis wind turbine. So type of rotor is not propeller motor. Only 7 years type is vertical axis wind turbine. Fixed speed wind energy conversion systems are equipped with squirrel cage induction generators. Okay, so use always remember this term. Now you have in mind that what is squirrel cage induction generator. This is what, where is the, oh, did it delete? Uh, Put a picture here. Huh, yeah, this one is here now. This is a squirrel cage wind generator. Okay, why it is called squirrel cage? Because there is a cage, copper winding outside the rotor. That and because of this copper winding, induction force is actually generated. So this induction force actually makes the rotor rotate. So this is why it is called squirrel cage induction generator. And why? Because losses are very less in this type of generator. They are very efficient. That is why we use a squirrel cage induction generator. Okay. A three-bladed wind turbine produces maximum power at the tip ratio. Power when the tip ratio is equal to. How much is the answer for this? So this has a very typical formula. You just have to 4 pi upon n. Okay, a three-bladed. So it's three-bladed. You put the value of n equal to 3. So 4 by 3 is 1.33. This is the formula. This is the question which I want you guys to approach and solve. A multi-blade wind turbine. So you have the solidity, you have the design wind speed also, you have the pump, the machine operates a pump, water pump, which has a capacity of this and lift of this, and the reciprocating pump has efficiency of 62%, transmission efficiency from rotor to pump in 92. Calculate the number of blades, consider the number of blades as 16, assume the rotor is delivering maximum power of CP at the design wind speed, blade length of this. So you have to calculate the radius of rotor. So only hint I will give, power of pump is, how much is the power of pump? Rho G AQ, is it? I am getting here so much mosquitoes here. Okay, so rho G HQ is the power of pump. Now this is the hint I can give. Rest all you have to calculate by yourself. Start calculating. Can I please? Yes, sure. I can go to the previous slide. Is this the slide? Okay. Okay. So now calculate this. You guys have 4 minutes to calculate this question. After that, I will explain this question to you guys. Okay. So I want you guys to defeat me. Mhm. So what is solidity? So actually, how will I explain here solidity? So solidity is basically some aerodynamic phenomena. I won't be able to explain it here because there is a graph, solidity graph to tip ratio graph. So because the shape of the wind turbine, we calculate the solidity ratio. Okay. So as of now, you just imagine that there is a solidity of zero point 0.5. So this is used to calculate the power of the generated by the wind turbine, which has a different aerodynamic shape. Okay. किसमें क्या करना है? हाँ हाँ, you will be using this solidity. This solidity is important part of this question. So the first question won't use any solidity concept. So I will explain you guys what solidity is actually. So solve this first question. In second question, the concept of solidity will be used. So I will explain, give you brief introduction about what solidity is. It's a very simple concept actually. Which one? This question? Okay. Let me explain you guys. So, okay. So the velocity, how much is the velocity? 22 kilometer per hour. But all our calculation is in meter per second. So you need to convert it to the meter per second. So it comes out to be 22 into 1000 upon 3600. Okay, so you do the calculation. 22 into 1000, 22,000 divided by 3600, 6.11 meter per second. Okay. Now we know the pump needs to lift this much capacity pump, 4.5 meter cube per hour, and the density of water is 1000 kg per meter cube. Okay, so pump will require rho g HQ to calculate the power of pump. So 1000 is the density, 9.81 is the G, and since this is in meter cube per hour, so you need to convert it to meter cube per second. So 4.5 meter cube upon 3600. Okay, and then Q you have H is how much is H? You have to lift it to 8 meter. So this comes out to be 1000 into 9.8 into this. This comes out to be 98.1 watt. Okay. Now what does it say? It says that uh, pump efficiency is 62%, transmission efficiency is 92%. So divided by 62% and then divided by 92%. So the correct power electricity which we need to give input to the pump will be 98 divided by this and divided by this, 171.98 watt. So this is the power which is required to run the pump, that is to be delivered by the wind turbine. Now you have to know the sorry, you have to get the radius of rotor. So for radius of rotor, what you will do? So for radius of rotor, you will need a graph actually. Keep. So if you will see the lecture slides, there is a graph. That graph is for CP, that is coefficient of performance, and tip speed ratio, that is lambda. So there is Savonius type of rotor, and for Savonius type of rotor, what is required? Number of blades. So assume the rotor is delivering maximum value of CP. So maximum value of CP will be here at this point. Okay, maximum CP. This comes out to be around 0.15. So from the graph in the lecture slide, you can see this is 0.15. So if CP is 0.15, so CP is, and for 0.15, the lambda is point, that is blade tip speed ratio is 0.8. Okay. So CP, what is CP? Basically the power required by the power in the wind turbine, that is rho wind, rho AVQ. Okay. Now you know the power 171.98, you know the CP value 0.15, 171.98, that is the required power for this required power, you need to have this 1.2 into, now density of wind is 1.2, velocity of wind, how much is the velocity of wind? 6.11, so 6.11 cube, and the area of rotor blades, that is pi into r square. So this is what is asked in the question, r square value, the radius of rotor. So calculate this r square value, r value. So 0.171.99 divided by 0.15 divided into 1.23 into 6.11. So this comes out to be around 1.63 meter. Okay. So this is the radius of rotor, 1.633. Correct? Any doubt? Now what is solidities? Ask, please ask. Hmm. Pi into L square, R square, R square. Three. This one, na? This one, R square. Wind turbine is 35 meter. So this is R long. You are taking it as L. You can take it as N. This is the length of the wind turbine. So if makes a circle, how does the turbine blades rotate in a circle? So if this is 35 meter long, so R will be 35 meter. R will be L equal to 35 meter. Are you getting my point? Huh, simple. Here also R and L will be same. Okay, the radius of rotor or the length of rotor is same. Which length? Acha, the braid length is, so you will assume this. What it is saying. How do I say it? Uh, you assume this one. This is the radius of rotor. Okay, so you have to calculate this one, R. Now you are clear? 1.4 meter is this one. Huh. It's not a width. Uh, Actually, if you see, it is in curvature. Do you have any pictures? You can see here. So this is actually in a curvature shape. So it does have a very good length also. Okay. Correct. Any other question? Now, what is solidity? So if you see solidity, solidity is actually blade area to the swept area. Okay, so blade area may be more, but the swept area will actually be less. So solidity actually tells us about that. I think this is what the blade length is. Okay, so blade length basically tells us about the blade area. This is not this area. Actually, this is like this only. So this is the blade length, but the whole area which will be swept is actually the on which the wind will actually work. So I think I'm wrong here. This is, if you get the concept of solidity. So let's say this is the blade. So this is the blade length 1.4. But actually when it rotates, it is not only the blade area but also some extra area which will it will sweep. So that also comes into it. So you have to calculate radius of the rotor here, that is swept area. Okay, and between the ratio between blade area to swept area is actually solidity. Okay, so it basically depends on the concept of lift and drag force. So if there is high solidity value, so it uses a drag force. Okay, and if there is low solidity value, then it uses a lift force to generate power. Okay, so this is how we classify the turbines also. Like if you have a 7 years turbine, it has a high solidity rotor, so solidity value for it is unity generally. Okay, so I think it's already too much of time, so I will ask you guys to solve this question by yourself. So if there are any queries, please feel free to ask your queries at this email ID. Okay, so thank you guys, thank you for attending this live session. We will meet again in the next live session on Tuesday from 7 to 9 p.m. Okay, thank you guys. Okay, I will upload the slides so you can access these slides from there also. I will upload it just now. Okay, thank you guys.